Power transmitted through fluid-filled pipes is the basis of hydraulic braking systems and other hydraulic control systems. Suppose that power associated with a piston moving at one end of a pipeline is transmitted by a fluid of density ρ moving with positive velocity v along a cylindrical pipeline of constant cross-sectional area A, assuming that the loss of power is mainly attributable to friction and that friction coefficient F can be taken to be a constant. Then the power transmitted P is given by this here. Now g is the acceleration due to gravity, that's 9.81 meters per second squared. H is called the head, that is the height of the fluid above some reference level. That's actually the potential energy per unit weight of the fluid. Remember, if we have a mass m at a height h above some reference level, then the potential energy is mgh, which is just the weight times the height. But if we're dealing with unit weight, then mg is equal to 1. So then the potential energy would be 1h, or just h. We also have this constant c, which is 4fl over 2gd, where l is the length of the pipe and d is the diameter of the pipe. The power transmission efficiency is the ratio of power output to power input. Assuming that the head of the fluid h is a constant, find the value of the fluid velocity v, which gives a maximum value for the power output p. So we have to imagine a fluid travelling in a pipe, but so the pipe would be horizontal presumably, because its head h is the distance of it above some reference point. So the reference point is this horizontal line here. So we see that the independent variable in this function is v, because ρ, g, a, h and c are constants. The dependent variable is p. We want the value of v that minimizes p. So to do that, we have to solve the equation dp dv equals 0. So this is straightforward. Ρ, g, a, h is a constant in front of v, so when we differentiate this first term with respect to v, we just get ρ, g, a, h. And when we differentiate this term with respect to v, we bring the 3 down, so we get minus 3c v squared. Minus 3c v squared times the ρ, g, a. We can leave that constant in front. So it's a straightforward polynomial in v, this function here, so it's easy to differentiate. We set the derivative equal to 0 and we solve for v. We can divide both sides by ρ, g, a, that's just a constant. So we get h minus 3c v squared equals 0. Or v squared equals h divided by 3c. Now we want v to come out to be positive, so we want the positive square root of h over 3c. Now this value of v will give us a stationary point for our function. It'll solve the equation dp dv equals 0, but we want this stationary point to be a local max. Now to show that we have a local max for this value of v, we take the second derivative. So we differentiate this expression here with respect to v. Well, ρ, g, a times h will just give us 0, that's just a constant. When we differentiate this with respect to v, bring the 2 down, we get minus 6c v times ρ, g, a. So we want to get the second derivative at this value v of root h over 3c. If we plug that in, well, this value of v is positive. And since ρ, g, a and c are positive, then and v is positive, then this thing is going to be negative. If the second derivative is negative, then we know that we have a local maximum at v equals root h over 3c. Now let's look at the picture. P is a cubic function of v. When v is 0, p is 0. That's fairly obvious from this, if you put 0 in for v. Root h over 3c, we have a local max. So the first derivative of p with respect to v is 0 at this point, and the second derivative is negative. Now we're interested in some range of v here. It's possible that we could get a value of p that is greater than it is at this value of v, but if we solve the equation p equals 0 to find out what value of v makes p 0, we get root h over c. So setting p equal to 0 here, this should be p here, and solving, we obviously get v equals 0, and the other value of v is root h over c. Root h over c is greater than root h over 3c. So for values of v greater than root h over c, well, at least for values of v in here, p is negative. So actually our model, I think, only works for values of v that make p positive. So anyway, we see that in the range of v for which our model is valid, this range here, we have only one maximum value. That's at root h over 3c. So our local maximum is the maximum for our function. Of course, if our model was valid for all values of v, then we would have a value of v that gives us a greater value for p somewhere over here, but I don't think it's valid over there, so we can ignore all of this. Suppose the input power is P sub I, is given by rho g AVH. Find the maximum power transmission efficiency obtainable. Well, we need to get the output power for the value of V that we just got. That is V equals root H over 3C. So the output power is given by this expression here, and we will plug root H over 3C in for V in the numerator here, and we divide by the given input power, rho g AVH. So simplifying here, breaking this down, the rho GA's cancel out, and we've HV over VH. Well, that's just going to give us 1. We have minus CV cubed over VH. That gives us minus CV squared over H. So that's the efficiency, and we want that at root H over 3C. So we need to plug this in. When we square it, we get rid of the square root sign. These C's cancel out. This should be a H. So the H's cancel out. We get 1 minus a third, which is 2/3.